Living on planet Earth with a sun in the sky every day can really desensitize us to what a star actually is. And for instance, sometimes even I forget that the sun isn't anywhere close to us. On average, the sun is located over 11,500 Earths away, just about 93 million miles, or 1 AU. When you look up into the sky on a clear night with little light pollution, you're greeted to hundreds of stars. But if you don't live anywhere near a city, however, and there's no moon in the sky, you could possibly see upwards of about 5,000 stars. Given so much stellar stimulus at once, it's easy to pass by the fact that lots of stars are very different at varying sizes, shades, temperature, and lifespan. Today, we're going to take a step back and soak up the hot topic that is stars. How does a star form? Call it a cliche all you want, but we're going to have to start at the beginning. Well, almost the beginning. It was 100 to 200 million years after the Big Bang. High-density clumps of matter with temperatures varying as small as 1/1,000,000th of a degree drew in clumps of other matter with less density. After those 200-ish million years, the clumps collapsed into stars, where so much matter had been brought together that the temperature reached at the star's center was hot enough for fusion to take place. In other words, the lighter elements can fuse into heavier ones. More on that in a bit. The pressure at the center of stars is so high that the temperature achieved is fiery enough to turn gases into plasma. Plasma is the fourth state of matter that can be described as an ionized gas made up of positive ions and free electrons with hardly any electrical charge. That's not too important for this episode, though. Groups of newly formed primordial clumps that would soon become stars are known as protostars. The clouds of matter where protostars exist are called protogalaxies. These will go on to form galaxies, and many galaxies would assemble into galaxy clusters, which make up small sections of the whole cosmic web. By the way, this is a process that's still going on to this day. However, it's a much less active factory than it used to be, to say the least. Leftover material would orbit the stars and eventually go on to form planets, asteroids, comets, or just remain in a dust-like state. The material orbiting a newborn star is known as a protoplanetary disk. Protogalaxies are significantly smaller than galaxies, taking up a region of only about 100 light-years, while our galaxy, the Milky Way, is about 100,000 light-years across. The largest known galaxy, however, IC 1101, is nearly 6 million light-years in diameter. That's 36 quintillion miles. Anyway, protogalaxies are mainly made up of dark matter, and since the Big Bang expelled large amounts of helium and hydrogen, the first stars would primarily be made up of these elements, and at the center of these stars, they would fuse into heavier elements. Today, the elements in the universe can be broken down into percentages in 3 different categories: 73% hydrogen, 25% helium, and 2% other. The presence of those two first elements really do show. The first stars were more massive than our sun and also burned much hotter, which caused their lifespan to be much shorter than that of our sun, and any metals formed during the fusion process were sent out when these stars went supernova.
No! I cannot believe this!
These metals made it much easier for the next batch of primordial clumps to collapse into stars, which is why the pace of star formation increased during the second set of stars. Researchers also believe the second group of stars is responsible for really lighting up the more or less dimly lit cosmos. Some early stars, which as mentioned were much larger than our Sun, managed to get 250 or more times larger than our Sun, which meant that they wouldn't go supernova at the end of their lives. Instead, they would collapse into black holes. Since these large stars were born in the densest part of the universe, these black holes could swallow each other up, growing larger and larger, to millions of times the mass of our Sun. You may have heard that most galaxies are believed to have a black hole at their center. In some cases, these are the same black holes scientists are talking about. Yeah, you heard that correctly. Some of the first black holes are still around today. The center of a galaxy is known as the galactic nuclei. This is where the densest region of stars and other objects are found, which are often much more luminous than any other part of the galaxy. Under the most common circumstances, once a star exhausts all of its hydrogen, the sun's core will collapse. But since hydrogen is still available outside of the core, fusion will continue beyond it. The increasingly hot center will go on to push the outer layers and cause the sun to expand and eject its outer layers until the stellar core is exposed. Quick-moving electrons will prevent the star from getting much smaller, but at this point the star is a white dwarf and will eventually go out entirely. The fate of stars can depend on whether or not it inhabits a binary or trinary star system and the amount of solar masses the sun has. Generally, there are 7 spectral types of stars, but you can also classify stars very specifically by their temperature, color, brightness, and size. I'm just going to scratch the surface though, for the sake of time. Before I start, let's quickly go over the Kelvin scale. 1 Kelvin is negative 457.87 Fahrenheit, or negative 272.15 Celsius. The conversion of Celsius to Kelvin is just K equals C plus 273.15. The conversion of Fahrenheit to Kelvin is a little more tricky, but here it is on screen. I'm going to be listing the types of stars from hottest to coldest. O-type stars are massive blue stars with a very high average temperature at about 40,000 Kelvin. B-type stars are blue-white stars with an average temperature of about 30,000 Kelvin. A-type stars are blue-white stars with an average temperature of about 10,000 Kelvin. F-type stars are white stars with an average temperature of about 7,000 Kelvin. G-type stars are yellow-white stars with an average temperature of about 6,000 Kelvin. K-type stars are orange stars with an average temperature of about 5,000 Kelvin. And finally, M-type stars are red stars with an average temperature of about 4,000 Kelvin. Our Sun is a G-type star, more specifically, a yellow dwarf with a diameter around 850,000 miles. Not only is it huge, the Sun is 300,000 times more massive than the Earth. The surface of the Sun is about 10,000 degrees Fahrenheit or 6,000 degrees Celsius, and the center of our Sun is about 27 million degrees Fahrenheit or 15 million degrees Celsius. It's 4.5 billion years old, and the Sun orbits the center of the Milky Way, which is 26,000 light-years away, or 153.4 quadrillion miles. The closest star system to us is Alpha Centauri, a triple star system located over 4 light-years from Earth, which is around 25 trillion miles. Alpha Centauri A, one of the stars, is very similar to our own in most ways. Alpha Centauri B is also very similar, but a bit smaller. The third star, Alpha Centauri C, or Proxima Centauri, is a red dwarf star. As far as I could find, NASA has only discovered one planet in Alpha Centauri named Proxima Centauri B. Considered a super-Earth, Proxima Centauri B is believed to be a rocky world located 1/20th of an AU from its parent star. It has a mass of about 1.3 Earths and was discovered in 2016. Know that the most powerful tool for learning is interest. Let me know what you're interested in. Maybe I can shine some light on it. All of my sources can be found in the description of this video, and as always, thank you for watching.